Welcome to the Deep Dive. This is where we take the topics you're curious about, dive into the sources, and pull out the key insights for you.
Yeah, think of it as a shortcut to getting up to speed without drowning in all the detail.
Exactly. And today, we're tackling something pretty profound.
We really are. We're looking at excerpts from Sean Carroll's book, Something Deeply Hidden, Quantum Worlds and the Emergence of Spacetime.
Right. And this isn't your typical physics textbook, is it?
No, not at all. It's more about the big picture, the different ways physicists try to understand what quantum mechanics means, the interpretations.
So our mission today is to unpack some of those core ideas, especially the ones that really challenge our everyday view of, well, reality itself.
That's the goal, focusing on where quantum mechanics clashes with common sense.
Okay, let's dive in. Quantum mechanics. I mean, even the name sounds a bit intimidating, right?
It definitely has that reputation. Difficult, mysterious, and honestly, even for physicists, it raises some deep questions.
So what's the central puzzle?
Well, fundamentally, it's this gap. There's a stark difference between the world we see and interact with and what quantum mechanics seems to be saying is really happening underneath.
A kind of disconnect between our reality and the quantum one.
Precisely. And bridging that gap, or at least understanding it, is a huge priority in science today.
It's not just abstract theory, then.
Oh, absolutely not. Quantum mechanics is incredibly successful. It describes how atoms, particles, forces work with amazing accuracy, makes predictions that are just unbelievably precise.
But the meaning is still debated.
That's the crux of it. What does the math actually tell us about reality?
Huh.
To really get why it's weird, it helps to think about classical physics first. Newton.
Right, the clockwork universe, apples falling, planets moving in predictable paths. Nice and orderly.
Exactly. Classical mechanics gave us these very clear, deterministic rules. Know the position, velocity, forces. You know everything, past, present, future.
That's Laplace's demon, isn't it? The idea of perfect prediction if you knew everything.
Yes, exactly. A perfect illustration of that deterministic viewpoint. If you knew the state of everything now, you could calculate all of history, forward and backward.
And crucially, measuring something didn't really change it in a fundamental way back then.
Right. A planet's position, its speed, these were just facts about the world. Observing them didn't introduce any weirdness, no measurement problem in classical physics.
Okay, but then we zoom in, way down to the level of electrons and stuff.
And that's where the rules change. Quantum mechanics takes over. Carroll makes the point, though, that even big things like rocks are fundamentally quantum. It's just that their quantum nature isn't obvious.
So what are the new rules?
Well, quantum mechanics introduces these extra rules specifically about measurement. When you measure a property like an electron's position or its spin.
Spin, like a little spinning top.
Sort of an analogy, yeah. Think of it like an internal compass needle. When you measure spin, you don't get just any direction. You only get specific, allowed results, maybe up or down, along the direction you measure.
Discrete results, like a light switch being on or off.
Exactly. But here's the kicker. Before you measure, you usually can't know which result you'll get.
You can only predict the odds.
Precisely. Quantum mechanics gives you the probabilities for each possible outcome, say 50% chance of spin up, 50% chance of spin down. But for a single electron, you can't know beforehand.
And then there's the collapse thing.
Right, wave function collapse. So the electron is described by this mathematical thing called a wave function, which encodes all the possibilities and their probabilities.
Okay.
But the moment you measure it, say you get spin up, the wave function instantly changes. It collapses so that it now only describes the spin-up state. All the other possibilities just vanish.
Poof, gone. And if I measure it again right away...
You'll get spin-up again, guaranteed. The measurement forced it into that state.
Which is just weird. Why does looking at it change things so dramatically?
That is the fundamental question. Why this difference? Quantum systems seem to evolve smoothly, predictably, according to this core equation, the Schrödinger equation, when we're not looking.
But the moment we observe, bam, collapse.
Exactly. How do they know they're being watched? Why do they care? It's like the universe gets stage fright, as Carroll puts it.
Okay, so the math works incredibly well for predictions, but the story it tells about what's really going on is confusing.
Deeply confusing. And that's why we have different interpretations. They're attempts to tell a coherent story that fits the math.
Trying to make sense of the recipe, not just follow it.
Yes.
Yeah.
The standard way it's taught is basically just the recipe. But people have been trying for decades to figure out, what's behind the recipe.
Were there early attempts to find, hidden gears?
Yeah.
Hidden variables. Einstein liked those, right?
He did. The idea was maybe the probabilities aren't fundamental. Maybe there are hidden factors, variables we just can't see, that actually determine the outcome. Like a trick coin seems random, but it's actually weighted.
So people like de Broglie, Bohm, Einstein himself explored
They
this.
did, trying to restore some kind of determinism, some classical intuition. But then came John Bell in the 60s.
Ah, Bell's theorem. This is where entanglement comes back in, isn't it? That spooky action at a distance.
It is. Bell figured out a way to experimentally test these hidden variable ideas, specifically local ones that don't involve faster-than-light influences.
And what did the experiments show?
Overwhelmingly, they showed that simple, local, hidden variable theories cannot reproduce all the predictions of quantum mechanics. Nature seems to behave in a way that's fundamentally spookier than Einstein hoped.
So it implies that either reality is non-local, there are instantaneous connections, or you have to give up some other core assumption.
Exactly. And while some non-local hidden variable theories, like Bohm's, still exist, they tend to be quite complex and face challenges integrating with things like relativity.
So if hidden variables are problematic, where does that leave us? What's Carroll's preferred path?
He champions what he calls austere quantum mechanics, or AQM. Most people know it as the aberration interpretation, or
Many worlds. The one where everything that can happen does happen, just in different universes.
that's the popular idea, yes.
Yeah.
Carroll calls it a courageous take.
Courageous is one word for it. How does it work?
The core idea is startlingly simple, in a way. It says the Schrödinger equation. It always applies. There's nothing special about measurement. It's just another physical interaction.
So no collapse.
No collapse. When a quantum system interacts with another, say, an electron hits a detector, or even just interacts with its environment, they become entangled.
Linked together.
Right. And the combined system evolves into a superposition of all the possible outcomes.
So the electron is both spin up and spin down, and the detector is simultaneously showing up and showing down.
In essence, yes. The whole system enters this massive superposition. And crucially, Carroll stresses, we shouldn't think of separate wave functions for each thing. There's one wave function for the whole entangled system, maybe even for the whole universe.
One giant wave function describing everything.
Potentially. And this wave function contains all possibilities. When the electron hits the detector, the wave function evolves to describe a state where both outcomes exist simultaneously within it.
But hang on, I only ever see one outcome. My detector says up or down, never both.
And that's where the worlds or branches come in. The idea is that due to a process called decoherence, which we'll get to these different parts of the superposition, the different outcomes, effectively stop interacting with each other.
They become separate.
They branch off. From the perspective of someone within one branch, like us seeing spin up, the other branches, spin down, become inaccessible, unobservable. The universe doesn't choose an outcome, it branches to accommodate all of them.
So there's another version of me right now in a parallel branch who saw the electron spin the other way.
According to many worlds, yes, that's the radical implication.
Wow. Okay. Courageous definitely fits. Taking the math seriously even when it leads.
Exactly. It embraces the simplest mathematical core, just the Schrödinger equation, and accepts the seemingly bizarre consequences for reality.
But it does raise a ton of questions, doesn't it? Like, when does the splitting happen? Is it instantaneous? What defines a world? How many are there? Are they real, like ours?
Absolutely. These are all active areas of discussion and debate within the interpretation. And maybe the biggest one. If everything happens, how do we explain the probabilities we observe? Why does the Born rule work?
It definitely feels like trading one kind of weirdness for another. So why go down this road? Why believe something so out there?
Carroll's point, echoing the White Queen, is that quantum mechanics itself forces us to believe seemingly impossible things before breakfast. These ideas aren't just pulled out of thin air. They're where the experimental results seem to lead if you follow the simplest mathematical description.
It's driven by the evidence, even if the conclusions feel strange.
Precisely. And a key piece of evidence was this realization that the classical distinction between particles and waves breaks down.
Right. Light, which we thought of as a wave, acts like particles, photons. And electrons, particles, act like waves.
Exactly. Quantum mechanics unifies these concepts. The fundamental reality, especially in quantum field theory, is described by fields. What we perceive as particles are really just excitations, like localized ripples, in these quantum fields. And everything is ultimately described by the wave function.
It's a long journey from Democritus and indivisible atoms.
A very long journey. Through Dalton's atoms, discovering electrons, the nucleus, protons, neutrons, quarks, constantly refining our picture of matter.
And in parallel, Understanding fields electric, magnetic, gravitational, Maxwell unifying electromagnetism.
Yes, and Newton and Laplace describing gravity using fields. The big leap for quantum mechanics was realizing these weren't separate categories. Fields can behave like particles, and particles like waves.
That started with Planck and Einstein, right? Quantized energy and photons.
That was the dawn, yes. Planck introducing quanta for light, Einstein running with the photon idea. Then came the old quantum theory, Bohr's atom model, with specific electron orbits, introducing Planck's constant as fundamental.
Which was a bit ad hoc, wasn't it?
We had issues, yes. The real revolution was the new quantum theory in the mid-1920s, Heisenberg's matrix mechanics and Schrödinger's wave mechanics.
Two different approaches that turned out to be the same theory underneath.
Remarkably, yes, mathematically equivalent. And Max Born provided the key insight. The wave function squared gives you the probability of finding the particle.
It's incredible how quickly that all came together, despite, the turbulence of the times.
Absolutely, a period of intense intellectual ferment shaped by experiments, philosophy, and world events. Science is definitely a human activity.
So back to the wave function, Carroll emphasizes it's smooth, not chunky, right? The quantum part isn't about discrete bits at the fundamental level.
That's his point. The wave function itself is a smooth, continuous mathematical object. The discreteness we observe, like energy levels or spin measurements, comes from how these waves behave, how they vibrate, so to speak, and how they interact during measurement.
And this wave function describes everything, leading back to entanglement.
Yes, in principle, one wave function for the universe connects everything. And Schrödinger's equation tells us how this universal wave function changes over time. The rate of change is tied to the system's energy.
Which also leads to the uncertainty principle. Can't know position and momentum precisely.
Exactly. It's a direct consequence of the wave nature. If you try to squash the wave function down to pinpoint the position, it inevitably spreads out in terms of momentum and vice versa. They aren't fixed properties the particle has, but potential measurement outcomes governed by this wave behavior.
Carroll also mentioned logic. Quantum mechanics doesn't break logic, does it?
No, not formal logic. His example of a particle in a box. The wave function can be spread out, giving probabilities for finding it on the left or right. It's tempting to say it can't be left and not left, but the allowed quantum state is a superposition representing both possibilities until measured. The logical statement, it's left or right, since it's in the box, remains true. It just challenges our intuition about how properties work.
That wave nature is clearest in the double slit experiment, right?
Yeah.
Sending electrons through two slits one by one.
The classic demonstration. Each electron makes a single dot on the screen behind particle behavior, but build up those dots over time, and you get an interference pattern stripes of high and low probability, which is classic wave behavior.
As if each electron somehow went through both slits and interfered with itself.
That's the puzzling part, but it gets weirder.
If you try to watch which slit it goes through,
The interference pattern disappears. If you measure which slit, the electrons just act like particles going through one or the other. No more wave interference.
watching changes the outcome. That's the core mystery again.
It really is. Wave-particle duality in action. Now, to make things a bit more concrete, Carroll uses particle spin. It's simpler than position momentum, but shows the quantum weirdness clearly.
Okay, spin. Not literal spinning, but an intrinsic property, like charge.
Exactly. The Stern-Gerlach experiment showed this. Send particles through a special magnet, and the beam splits based on spin, say, into up and down, quantized.
And if you take the up beam and send it through another magnet, but oriented sideways,
It splits again into right and left. Even though you knew it was up vertically, its horizontal spin was undefined until you measured it horizontally.
so spin direction depends entirely on how you measure it.
Precisely. Any spin state can be thought of as a combination, a superposition,
Yeah.
of basis states like up, down, or right, left. Like mixing colors. Mathematically, we use vectors.
And the probabilities, the Born rule, connect to the lengths of these vector components.
Yeah, there's a nice geometric picture using the Pythagorean theorem, essentially.
Mm.
The squares of the components' amplitudes add up, representing the probabilities.
Okay, got it. But back to Einstein's spookiness. Entanglement was his real issue, more than uncertainty.
Carroll argues, yes, it wasn't just randomness he disliked, but this non-locality, the apparent instantaneous connection between distant entangled particles.
Which happens because there's just one wave function for the combined system.
Fundamentally, yes. If two particles interact, they become described by a single entangled wave function. Measuring one instantly tells you something about the other, no matter how far apart they are.
Like the correlated electrons example. Measure one spin up, you know the other is spin down instantly.
Exactly. Seems like information is traveling faster than light.
But the no signaling theorem says you can't actually send a message that way.
Correct. The correlation is instant. But Alice can't force her electron to be spin up to send a 1 to Bob. She gets a random result, which is correlated with Bob's random result. Bob only knows what Alice got if she tells him later, classically. So, no faster than light communication.
But still spooky, this led to the EPR paradox paper.
Yes, Einstein, Podolsky, and Rosen argued, if quantum mechanics is complete and measurements have definite outcomes and there's no spooky action at a distance locality, then particles must have predefined values for all properties simultaneously, elements of reality.
But uncertainty says you can't know vertical and horizontal spin precisely at the same time.
Exactly. So EPR concluded, quantum mechanics must be incomplete. There must be hidden variables determining these properties.
Enter Bell's theorem again, the experimental test.
Right. Bell showed that any theory based on local hidden variables predicts certain limits on how correlated the measurements on entangled particles can be. Quantum mechanics predicts correlations stronger than this limit.
And the experiments.
They consistently violate Bell's inequality and match the quantum predictions, even very sophisticated loophole-free tests. It strongly suggests reality is non-local in this quantum sense, or we have to abandon realism about properties before measurement.
How does many worlds handle Bell's theorem and this non-locality?
It sidesteps the issue in a way. The assumptions Bell used, particularly, that measurements have single, definite outcomes don't hold in many worlds. When Alice measures her particle, the universe branches. In one branch, she gets spin up and Bob gets spin down. In another, she gets spin down and Bob gets spin up.
So the correlation isn't spooky action, it's just consistency within each branch.
Exactly. The correlation arises because both outcomes happen in different branches, maintaining the link established when the particles became entangled. It's correlation via branching, not via instantaneous influence across space.
Okay, let's unpack that branching more. You mentioned decoherence. How does that work?
So when a quantum system, like our electron, interacts with a measuring device, or even just its environment, air molecules, photons, anything, it gets entangled with them.
It's not just the electron and the detector anymore.
No. The entanglement spreads rapidly into the environment. The different parts of the electron's wave function, spin up versus spin down, get tangled up with different states of potentially billions of environmental particles.
And this mess prevents the different possibilities from interfering with each other.
That's the key. Decoherence. This entanglement with the environment effectively scrambles the delicate phase relationships needed for quantum interference. Think back to the double slit experiment.
If you measure which slit, the interference vanishes.
Right. Measuring means entangling the electron with a detector, which quickly entangles with the environment. Decoherence happens, destroying the interference. For all practical purposes, the different possibilities, electron went left, electron went right, behave like separate classical outcomes.
So decoherence is the process that makes the branches of the many worlds effectively separate and distinct.
Yes, it explains why we don't see macroscopic superpositions, like Schrödinger's cat being alive and dead. The cat interacts so strongly with its environment that the alive and dead branches decohere almost instantly, becoming distinct worlds from our perspective within one branch.
So in many worlds, measurement isn't some special process. It's just any interaction causing entanglement and decoherence.
Pretty much. The Schrödinger equation rules everything. Measurement is just physics interaction, entanglement, decoherence, branching. No collapse needed.
And the observer doesn't need to be conscious. A Geiger counter, a rock, anything interacting.
Anything complex enough to interact and cause decoherence. Macroscopic objects are constantly decohering because they're constantly interacting with their environment. It happens incredibly fast.
The elegance is removing the collapse rule, but the price is countless parallel worlds.
That's the trade-off. Carroll acknowledges the history. Everett's PhD, Wheeler's initial support then caution, Bohr's resistance. It was a radical idea, and the shut-up-and-calculate attitude dominated for a long time.
Okay, but the probability question still looms large. If all outcomes happen, why does the Born rule, amplitude squared, give us the right odds within our branch?
This is arguably the trickiest part for many worlds proponents. The traditional frequentist view of probability, relative frequency over many trials, fits well with the collapse picture, but less obviously here.
Right. If you flip a quantum coin 100 times, there are branches with all heads, all tails, and everything in between. So what does 50% probability mean?
The modern approach within many worlds often uses an epistemic or Bayesian view. Probability isn't about frequency, but about an observer's rational degree of belief or credence.
My belief about what? About which branch I'm on.
Exactly. After a branching event, there are multiple copies of you. None of them knows which branch they've landed in immediately. This is self-locating uncertainty. The argument, quite technical, is that a rational agent in this situation must assign credences to the branches according to the Born rule, amplitude squared, to be consistent. Any other assignment leads to betting strategies that guarantee losses, essentially.
So the Born rule emerges not as a rule about frequencies, but as the unique rule for rational belief when facing quantum branching.
That's the claim. It's a subtle, but, proponents argue, powerful argument deriving probability from the structure of the wave function itself plus principles of rationality.
Still feels like a lot to swallow. What other objections does Carroll tackle?
Well, the big one. It's just crazy. It violates intuition. The reply is, quantum mechanics is crazy. Many worlds just follows the math where it leads.
What about Occam's razor? Isn't adding infinite universes less simple?
Carroll argues the formalism is simpler, just Schrodinger's equation. No extra collapse rule. The complexity is in the state, the wave function, not the laws. He also addresses the baggage objection, all that information. Again, the underlying math space, Hilbert space, is the same size in any interpretation. Many worlds just says all of it is physically relevant.
And the energy? Where does the energy for new universes come from?
It's conserved. The total energy of the universal wave function remains constant, according to Schrödinger. It just gets distributed differently across the branches. It's not creating energy from nothing.
What about time's arrow? Or worlds merging?
Time's arrow is likely tied to the universe's initial low entropy state, same as in classical thermodynamics, Carroll suggests. Worlds merging back. Theoretically possible if decoherence reverses perfectly, but fantastically improbable for anything complex. As for how many worlds, fuzzy depends how you count, especially for continuous variables. Infinite, perhaps, in some sense.
So many worlds provides answers, but they often involve accepting these really large-scale, counterintuitive consequences. It's definitely not the only game in town.
Oh, absolutely not. Carroll acknowledges the shut-up-and-calculate era and the resistance faced by people working on foundations. But that work continued, leading to alternatives.
Like theories that do have a real collapse.
Yes, dynamical collapse theories, like GRW. They modify the Schrödinger equation itself, adding a mechanism for spontaneous collapse that becomes more likely for larger systems. So microscopic things stay quantum, macroscopic things collapse quickly.
And refining hidden variables, like Bohmian mechanics.
Right. Bohmian mechanics posits both the wave function, guiding the particles, never collapsing, and definite particle positions at all times. It reproduces quantum predictions, but is explicitly non-local.
And the really different ones, like cubism, where the wave function isn't even real.
Exactly. Epistemic approaches like cubism, quantum Bayesianism, say the wave function isn't about reality itself, but about an agent's subjective beliefs and probabilities concerning future experiences. It's a tool for updating beliefs, very observer-centric. Each interpretation tries to resolve the puzzles differently.
It's clear the debate is far from over. Thinking about many worlds, though, what does it imply for things like, well, us, personal identity?
It gets weird. If you branch, are those future versions still you? Carroll suggests they become distinct individuals sharing a past, your future branches, but your past is unique, thanks to the universe's initial simple state.
Any ethical implications? If all outcomes happen, does it matter what I choose?
Carroll touches on this. It might complicate certain ethical frameworks like utilitarianism. How do you weigh happiness across branches? But for practical, everyday morality, he argues it probably changes very little. Your actions still determine the nature of the branches you create and inhabit.
What about free will? Does quantum randomness give us free will?
Probably not in a simple way. Quantum effects might be happening in the brain, but random firings don't equate to conscious choice. In many worlds, the branching itself is deterministic based on the wave function's evolution. It's not you choosing the branch, but the physics causing branching based on your brain state.
And consciousness itself. Does many worlds need it?
No. Unlike some older interpretations that seem to give observers a special role, Everettian mechanics is purely physical. The observer causing branching can be anything. Consciousness remains a separate mystery, the hard problem, regardless of your quantum interpretation. Carroll also briefly discusses philosophical idealism, mind is fundamental, and finds it struggles against scientific evidence.
So ultimately, what is real in this picture? The wave function.
Carroll argues strongly for wave function realism, especially within the many worlds context. Quantum field theory tells us fields are fundamental. Many worlds says the universe is the evolving wave function in this vast mathematical space, Hilbert space.
But the worlds themselves, are they fundamental or just a useful description?
He leans towards them being an emergent description, like describing a fluid using pressure and temperature instead of listing every molecule's position. Worlds are patterns that emerge from the underlying wave function after decoherence. They capture the macroscopic reality effectively.
Emergence. Like a chair emerges from atoms, worlds emerge from the wave function.
That's the idea. Emergence isn't subjective. It's finding simpler, higher-level descriptions that are still accurate and predictive within their domain. It connects back to Schrödinger's cat. The alive and dead states emerge as stable, decohered patterns within the total wave function entangled with the environment.
This idea of emergence, could it apply even to space and time?
That's the really cutting-edge speculative frontier Carroll explores. Quantum field theory has this strange vacuum state, not empty, possibly with huge energy. Maybe space itself isn't fundamental.
How could space emerge?
One idea relates to entanglement. Maybe the amount of entanglement between fundamental quantum degrees of freedom defines distance. Highly entangled means nearby. Weakly entangled means far apart. The geometry of space could be a map of the entanglement structure.
So gravity might emerge from quantum entanglement.
It's a research program. Jacobson showed you can derive Einstein's equations from thermodynamics and assumptions about entanglement entropy, like the Bekenstein-Hawking entropy of black holes. It hints at these connections.
And time, could that emerge too?
Possibly. The fundamental Schrödinger equation describes evolution in time, but maybe time itself isn't fundamental. Some approaches to quantum gravity suggest a timeless underlying reality. Time could emerge from correlations, perhaps how a clock subsystem gets entangled with the rest of the universe within the static overall wave function.
This feels deeply connected to the black hole information paradox. Hawking radiation seems random, erasing information, which violates quantum mechanics' core principle of information conservation, unitarity.
Exactly. Understanding how information gets out, or if it does, how black hole entropy relates to entanglement across the horizon. These are key drivers for quantum gravity research. Many worlds, being strictly unitary, information is always preserved in the total wave function across all branches, might offer a natural framework for resolving this.
So even if physicists aren't explicitly saying many worlds, the tools they use, entanglement, unitarity, might be implicitly pointing in that direction for quantum gravity.
Carroll suggests that yes, the focus on entanglement, entropy, holography, deriving space-time from quantum information, these ideas resonate strongly with the Everettian picture of reality being fundamentally about the quantum state.
It's a staggering thought. Everything, space, time, us, emerging from this underlying quantum function.
It is. Carroll wraps up by reflecting on the wonder, quoting Einstein. He reminds us tools like Feynman diagrams are useful stories, calculations aids, not literal pictures of particles bouncing around. Virtual particles are mathematical constructs.
And our current theories are effective field theories, useful approximations that work well, but likely break down at extreme energies.
Exactly. Acknowledging our limits while celebrating the incredible success we've had. The ultimate message is, reality is quantum. Our classical world is an emergent approximation. Many worlds, for all its weirdness, offers perhaps the most straightforward way to take that quantum reality seriously.
Okay, so wrapping up this deep dive based on Sean Carroll's work, we've grappled with the core mystery of quantum measurement, explored many worlds as a potential solution that eliminates collapse but spawns universes, seen how entanglement and decoherence are key, tackled the puzzle of probability, acknowledged the alternative, and even peeked at how space and time might emerge from quantum foundations.
It's been a journey into some truly fundamental questions about reality, tailored from the source material you provided.
And maybe, as you go about your day, just let these ideas simmer. How does thinking about reality as potentially branching or fundamentally quantum shift your perspective, even just a